This is Neil Patwari. In this segment of ESE 471, I'm going to talk about MIMO, and the message is going to be don't put all your signals in one channel. And this goes back to what we were talking about in the last video segment, where we talked about how any multipath channel might have a random gain, depending on exactly where the antenna is with respect to the multipath components. You saw these videos of multipath being added together, and at any given time, there's some kind of distribution of where those amplitudes of the multipath channel might be. We're going to call this amplitude gain H, and H is for any particular pair of antennas, there's going to be a gain between them. So when I have multiple antennas, I'm going to have multiple values of H. So for example, if I have two transmit antennas labeled antenna 0 and antenna 1, and I have two receive antennas labeled antenna 0 and antenna 1, then I would have four different channels between each pair of antennas. We're going to use HIK to represent the gain of the channel between transmit antenna K and receive antenna I. What we're going to explore in this video is how we can use either one transmit antenna and multiple receivers, how we can use multiple transmitters and one receive antenna, or we can go multiple transmit antennas and multiple receive antennas. And these are different cases of the same concept that we don't want to put all of our signals in one channel. In fact, we want to gain from the diversity of having multiple random realizations of the gains in this channel. When one goes bad, hopefully some other channel is going to be good, and that's going to allow us to recover our transmitted signal. And in fact, we're going to show that having a multipath channel is a benefit, because when I use these multiple input or multiple transmit antennas and multiple output or multiple receive antennas, that allows me to gain from the multipath in the environment. And in general, this area is called MIMO, or multiple input, multiple output. Let's start with the case where I have two receive antennas and one transmit antenna. My transmit antenna is going to send S. Usually we've called this S of t, and we talk about how S of t is a sum of time-delayed, amplitude-modulated pulse shapes. And in this case, just to keep things simple and to keep ourselves aligned with the literature that you're reading, we're going to remove the t, and we're just going to talk about S. And if you want to put the parentheses t back in for the transmitted signal, or in fact for the received signal, which will also leave out the parentheses t, you can do that, but right now I'm going to leave out the t. Our received signal is going to be x0. It's going to be the H0 channel between transmit and receive antennas 0 and 0, multiplied by the transmitted signal, plus some noise, and we're going to call W the noise, and we're assuming again some Gaussian noise added to this. We have another antenna, 1, that is going to experience a different channel, H10 times S, and a different noise. And what we do in this case, to get the best situation we can out of our signals X0 and X1, remember we're trying to estimate S, we don't want the noise, but we want S, even if H00 is very small or H10 is very small, we want to get a good estimate of S. So what we're going to do is we're going to come up with an estimate for S that combines some amplitude multiplied by x0 and some amplitude multiplied by x1. In a scheme called maximal ratio combining, or MRC, we multiply x0 by h00 conjugate, and then we add it to h10 conjugate times x1. Let me plug in the values for x0 and x1, and h00 conjugate multiplied by h00 becomes h00 magnitude squared. So we get, instead of one amplitude multiplied by S, we get the sum of the squared value of two different channels, h00 and h10, and those two add together but when they multiply the signal S. In contrast, the noise is multiplied by a sum of two complex values of the two channel gains, but it doesn't add together as the sum of their powers. And thus the signal to noise ratio increases here for our estimate S hat. Although there's still noise, the power in the signal raises more than the power in the noise. And so we get this is called maximal ratio combining because it produces the highest signal to noise ratio possible given these two received signals. It allows us to recover if one of these two channels has low amplitude. But that's if I have two receive antennas and one transmit antenna. What Alamouti showed was that we can achieve this same diversity when we have two transmit antennas and one receive antenna. So now we've got two transmit antennas and one receive antenna. The Alamouti coding scheme says that what we're going to do is we're going to achieve diversity by sending two different symbols over two symbol periods. We're going to call these two symbols S0 and S1. These are sent at different times. First, we're going to transmit S0 from antenna 0, and we're going to transmit S1 from antenna 1. This is during the first symbol period. During the second symbol period, we're going to send minus S1 conjugate from antenna 0 and S0 conjugate from antenna 1. This first symbol period, we're going to receive X0 at our single antenna receiver. During the second symbol period, we're going to receive X1 again during that second symbol period. And these two are going to add together in a linear combination based on those channel gains. So X0 is going to be equal to H00 times S0 plus there's another channel H01 multiplying by the signal S1. Well, we're talking about this H01 and H00. So X0 takes that form, and X1, it's the same channel, but instead of S0 being sent, it's minus S1 conjugate and S0 conjugate being sent. And what we're going to do in the Alamouti scheme is we're going to form these particular linear combinations of X0 and X1 in order to estimate S0 and S1. Okay, how does this work? Well, S0, if I plug in for X0 and X1 based on the above formulas, I'm going to get the following. Okay, these two terms are just opposites of each other. We've got the H00 conjugate in both, multiplied by the H01, multiplied by S1, and this one has a minus sign, so these two are going to cancel. And we're going to be left with an amplitude scaled version of S0. We could estimate S0 by dividing this S0 tilde by this constant. These two terms cancel, and we're left with an amplitude scaled version of S1, which again we can estimate S1 by dividing S1 tilde by this sum. What this means is that the signal that we receive, that we estimate for symbol 1, has a factor that multiplies by one channel squared plus another channel squared, instead of having one or the other channel that is multiplying our signal. And thus, it allows us some diversity gain. That is, we are much less likely to have a deep fade, causing our signals to be lost. And what I'm going to tell you next is something that is even better. So when we have full MIMO, we have multiple antennas at the transmitter and multiple antennas at the receiver. I'll stick with two antennas at both the transmitter and receiver for this example, but you can imagine that we could have many more than two antennas at each transmitter and receiver. So we're going to define these vectors S, S0 and S1, and all the way up to SNT, if I have NT transmit antennas. We're going to define the noise vector as being the same length but for the noise. We're going to have a channel matrix H that has nt columns and nr rows, and we're going to have a receive signal that is nr length. And here again, we're studying the 2 by 2 channel, but in general, our formula is going to be that this matrix H multiplied by vector S plus some noise becomes our received signal X. We're going to talk first about a method of MIMO called direct mapped MIMO and an algorithm called zero forcing, that simply what we do is we take this equation for our transmitted signal multiplied by the channel matrix, which turns it into our received signal. We're going to take that received signal and we're going to multiply it by H inverse, and that's going to give us an estimate of our vector S. Okay, now if I plug in for X as in this equation, I get H inverse times H times S plus W, and if this is in fact a matrix inverse, H inverse times H becomes the identity matrix, and I just get vector S back. And my noise gets multiplied by this inverse matrix. Let's get an example for our 2 by 2 matrix. H inverse is equal to, what happens here, I point this out, this is called the determinant of H. And if you remember from your linear algebra, this is the product of the eigenvalues of H. And I point this out because if this is very close to 0, then this constant becomes very high, and what we're effectively doing is multiplying our noise vector by a large number, a large valued matrix. And this constant, the determinant, becomes close to 0 if any of the eigenvalues of H are close to 0. If we have an indeterminate matrix or an ill-conditioned matrix, we end up with a poor solution. And there is a method called the minimum mean squared error algorithm that can be used to find the solution to estimate S, which is discussed in the reading for today. That MMSE receiver will be more robust. So in comparison, in receive diversity, we use multiple receive antennas, but one transmit antenna, and we're able to achieve diversity gain from our 2 channels. In transmitter diversity, we use 2 antennas and 1 receive antenna. We can use the Alamouti code scheme or some variety of that scheme to achieve diversity gain over 2 symbol periods to get the same average symbol rate out of our system. But finally, in MIMO, what we're actually doing is we're actually sending 2 symbols at the same time on our 2 different transmit antennas, receiving some linear combination on the 2 receive antennas, and using that then to figure out what was sent on those 2 transmit antennas, effectively adding more what are called eigen-channels. And these eigen-channels correspond to the eigenvectors of the channel matrix H. And in fact, if we talk about the eigenvectors of the channel matrix H, then we can talk about how MIMO increases the capacity. Okay, we're going to define capital N as the minimum of the number of transmitters and the number of receivers. And we can show that this matrix H transpose, or sorry, H Hermitian, that is the complex conjugate of the transpose, these have eigenvalues that we're going to label as lambda I. There are capital N of these eigenvalues and corresponding eigenvectors. And effectively what happens is that the Shannon capacity for the channel becomes a sum of n different channels. That is, the channel efficiency compared to Shannon's bound, which was the log base 2 of 1 plus the SNR. Now we have equal to a sum from I equal 1 to n of the expected value of the log base 2 of 1 plus SNR multiplied by this lambda I eigenvalue divided by n. And here, the lambda I are random because of the channel. The statistics of the channel will determine the expected values of these lambda sub I. But effectively what happens is we have these eigenvalues multiplying the SNR and then contributing to independent data rate or efficiency, spectral efficiency, on each of these capital N channels, and N being the minimum of the number of transmit and number of receive antennas. So if we have more than one transmit antenna and we have more than one receive antenna, we can effectively multiply the capacity of our signal. Effectively, we get about N times the capacity on a single channel. In practice, it depends on having a lot of multipath, so this won't work on a space communication link. It also won't work if we increase the value of N very, very high, because in effect, the number of multipath in the channel and the variety of multipath in the channel will limit our attempt to take advantage of the MIMO capacity gain. So this is our topic of don't put all your signals in one channel. If we use multiple channels by having multiple antennas at the transmitter and receiver, we can really do a remarkable job of increasing the spectral efficiency of our communication systems.